So hello everyone, welcome back to this class. So in this class we will discuss about the PID controller and how to actually find out the gain of a PID controller. So this is a very important lecture. Please be careful while attending this lecture. Okay. So PID controller, you might have heard this name, where P is proportional, I is integral and D is a derivative. So now the question is, what P generally does, what I does, or what D does. Okay. For example, let's say I want to move from point A to point B. Want to move from point A to point B. Okay. So now you will estimate the error between point A and point B. Let's say the reference is this, and this is actually your current state, and this you actually want XC is commanded. Okay. So what is the error? Error is X command minus X. This is error. Okay. Now if you want to move from point A to point B, you have to move with velocity, right? Some velocity, right? So let's say you commanded your velocity with this error, some constant k into xc minus x, or you call as a ke. So when you increase k, your commanded velocity will be more. So you will move faster from point A to point B if your plant is supporting whatever you are commanding, and from by putting the legs forward, you are able to generate that much velocity. So that means if you increase the k, you will move from point A to point B faster, right? If you reduce k, you move slow. So this case, which is directly associated with the error only, it's called proportional term. Okay, generally called Kp. So P part is clear, right? And I want to discuss more about the P part. When you reach from point B, so you will move ahead of point B, right? And then the error will become what? So let's say this was the error. This error was positive, right? So when you reach from when you cross this point, and if you reach here, then you have this much error, right? Let's say E dash. So again the controller will try to bring you back at the point B, and again you will shift from this point. So we'll keep oscillating, right? So that is why by using P only you cannot hold the position at B, and if you increase the P, your oscillation will be keep going on, increasing and increasing. For example, let's say this is the first case where Kp was slow actually. Then the oscillation can be like this. For example, you want to reach this point B, right? And this is the point A. So now you have reached this point and you keep oscillating, right? But if you increase the K value, the oscillation may increase, right? Something like that. Only using P you cannot actually attain the point B. And you can consider the example of quad rotor case. By simply using P, you cannot hover. Let's say this is your desired height. Okay, so by using P, you will reach this point and you will try to overshoot, and then come back again, undershoot. So overshoot, undershoot, overshoot, undershoot will be keep going on, keep going on, keep going on. So one thing it is clear, from the P we can reach nearby the P, and we can also control the response time. By increasing the Kp value, you will move faster, right? That is clear about the P, right? Now, when you take E dot, for example, like a, let's say Kd into E dot part, see Kd is a, see Kp into E is proportional part. Now I will add Kd into E dot. That means you are controlling the rate of error. If you differentiate, that means what you are controlling, basically you have a control over a velocity. So that means actually you can reduce the oscillations. Actually you can reduce the oscillation. So that means you can actually smoothen your curve. But again the question, you cannot hold at a point B. Okay. So what you will do? You will use the integral. So Kd is used for smoothen the curve, right? And Ki used for eliminating the steady state error. So you can see from this diagram, let's say I have this kind of response. Now if you want to control this, let's say this is the closed loop controlled response. Okay. Now the Kp is responsible from reaching to 0 to 1, but with oscillation we have seen, right? By introducing Kd, you can actually smoothen the curve. You can actually smoothen the this curve, and you have some steady state error. Steady state error means you are actually not at that point. You have eliminated the oscillation, but you are not exactly at the point B. For example, you have commanded 5 meter, but instead you have reached 4.98 or 4.97. So the integral part will try to eliminate the steady state error. So what is 5 minus 4.97 is a steady state error only. So now you can see how proportional, you can see, is a current one, right? And derivative is predicting the future error. And now integral is looking back and trying to eliminate the steady state error. So that is a job of PID. We can say, now how will you draw the same in the block diagram? This is my plant and I am putting in this block. Say this is the aircraft or spring mass system in system. Okay, now initially you were giving the input and receiving the output, but you want to control as per as the requirement to reduce the settling time, minimize the overshoot, rise time, peak time. So naturally it is not possible, so you have to use the controller. And even if the system is unstable, then you have to have used the controller, right, in order to fly the vehicle. Now, so what I am inserting the input, now this will not come directly, this will be the driven by PID controller. How you supply the correct input in order to control your vehicle. That is input is PID only, right? So now I will put 3 block here. One is P and one is D and one is I. So now this is your some set point. Let's say you have commanded Y, command something. That can be the angle, that can be the altitude, any other parameter. This is the Y, and now you will take the error and you will supply to this 3 block. This is Kp, Ki and Kd. So you have to take the derivative action, right? Or I will put the plant in the middle so that you can actually have a good visualization. You will take integral action, and here you will take derivative action, right? So you will differentiate here. You can put actually s is the derivative only, right? So now you can see initially in my plant I was inserting input and I was getting the output. But now how, based on the set point, I am supplying the input by using the PID controller. So this is the PID controller U, and U you can write what? Kp into E plus Kd into E dot or plus Ki into integral E. That you can write actually. Okay. Proportional action, integral derivative action, and integral action. So by 3 action you can actually supply the input U to the plant in order to get the desired response. First question is how this gain you will select, and what are the impact of this gain on a system response. So one thing is clear, by increasing the proportional gain you will make the system response faster. So now we can see, if you want to reduce the peak time, rise time, okay, this means you want to shift the curve in this direction, you have to increase the proportional. Okay, and now while doing this, for example, like if you want to reduce the rise time, so while reducing the rise time, what you will do? You will try to increase the proportional, okay, and in order to smoothen the response, you will reduce the derivative gain, okay, and also if the system response is faster, you will reduce the integral action, okay. Integral is very careful, you have to be very careful while using the integral gain. So in integral gain, if you use in a proper fashion, it will support you, and if you are not using in a proper manner, that means it can lead to the system failure, complete disaster, if you are not using the integral in a proper fashion. For example, let's say you have commanded some angle, by that time your control surface has saturated, so error will be keep on adding, right? Keep on adding. So this value will be U will be value is what? Kp into E plus Kd into E dot plus integral Ki into integral E into dt. So because of this integral action, your U value is keep going on increasing because error is summing up, right? So that is why it is very dangerous at the time of when the actuator saturates. For example, you commanded the thrust to hover the vehicle, and the time motor got saturated. So in this condition, if you are not limiting the value of integral gain, So it will keep providing the control input, control input, control input, and you will not be able to recover the system back to the normal flight condition. So you have to be very careful in the integral, because it's an integral e into dt, right? Error is summing up, right? So u value will be keep on increasing, right? So that is why you have to put the saturation block. Even if my command is this much, but I will not provide at all. That is why you have to limit the output, you have to limit the input in order to perform the controller within the acceptable regime. For example, like we generally do not command 70-degree band suddenly, right? We generally put the saturation plus minus 30, plus minus 50, right? And even, for example, let's say if the elevator is, we can deflect the elevator 10-degree up, 15-degree down, okay? Beyond that we cannot deflect, right? See, we cannot rotate 360-degree, right? We can, it's meaningless, right? But controller is a math block. So if you provide the, if you not do the proper algorithm, then it may provide, okay, deflect 30-degree. Can you deflect 30-degree or 360-degree? Meaningless, right? So you have to limit. So that is why you have to limit the saturation, that beyond this, even if it is commanding, but you never deflect that much. So that is the part of integral. So what I'm trying to say, if you want to reduce the settling time, then you have to reduce the KD and increase the proportional. And at the same peak time, let's say, so if you want to reduce the peak time, then what you will do? One thing is clear, you will increase the proportional constant. But at the same time, in order to reduce the overshoot, you will increase the KD value. And here, in this case also, you will reduce the KI value. Now, when you increase too much KD, there is a problem, very sensitive to noise. And if you reduce KD value very low, in the first case, rise time case, then system may become the unstable. So you have to be very careful what amount of gain you are selecting, what you are putting. So that is the significance of PID individuals. Right? Now the question is, how will you select? How will you select this value? So one thing is very clear. If you don't know anything, do the hidden and try. But it's a 3 gain. So many combination will come. It is not a proper way to do the gain, selecting the gain. So instead, what you can do, you can use Ziegler-Nichols method in order to tune your controller or find out the initial gain. So I will tell you the Ziegler-Nichols method for finding out the gain. So in this case, what you will do? Okay, one thing is clear, right? By increasing the proportional gain, you will get the oscillation, right? So you, in this method, you try to first oscillate the system. Let's say you have any system like this system, right? Plant, spring mass system, or aircraft, but you don't know the gain. You don't know the gain. So what first you will do? Okay, first my job is reach to that position. Forget about the oscillation and reducing the oscillation and reducing the steady state error. First my job to reach from point A to point B, right? So I will first focus on KP gain. My focus will be only on KP gain. Let's say this is the plant. And this is my set point. When I say set point, that means what we are commanding actually. That is a set point. Okay. So now in Ziegler-Nichols method, what is the next step? You will keep on increasing the gain, because we know that by increasing the gain, you will get the oscillation. So increase the gain until you get this kind of neutrally stable case. Let's say this is a neutrally stable case, and you measure this time. This is T. Okay. So you keep on increasing the gain until you get this response, neutrally stable case. So once you get the response, stop here, and based on this selected gain value where you got this response, you can actually select the Kp value, which is 0.6 into K. And if you do not want to do the hit and trial by increasing this gain, what you can do plot the root locus, and you can see where the root is crossing at this imaginary axis. Select that gain and put here, directly you will get the oscillation, because it's an imaginary axis, right? Will keep oscillating, right? The Ki gain can be selected 1.2 into K divided by T. So this is Ki, and Kd you can select 0.075 into K into T. And if you do not want any overshoot, for no overshoot case, for no overshoot case, you can select the Kp as a 0.2 into K, slow gain, right? And Ki 2 by 5 K by T, and Kd okay, Kd you can select K into T, 1 by 15 K into T. If you do not want overshoot, you can select this Kp, Ki and Kd like this. This is based on the uh, uh, experimental method. This gain value have been find out, this coefficient 0.2, 2 by 15 and 1 by 15, and for this case Kp is 0.6 K. Now you can see, when you do not want overshoot, you have to reduce the gain, right? See, this is 0.2 into K and this is 0.6 into K. Okay. So this is, by using the Ziegler-Nichols method, you can actually select the Kp, Ki and Kd value, and you take any system and it will give you the promising results. Now, once you select this gain, you can put in this block Kp, Ki and Kd, and you can actually get the response what actually you want. But be careful, you do not supply you directly to the plant, because this has some physical constraint. For example, if you in aircraft case, let's say you are deflecting the elevator, you can deflect the elevator plus 10 degree up and minus 15 degree down. But if the in computation, if you are getting 20 degree or let's say 50 degree, you cannot supply this directly to the plant, because this is a math block. So you have to be very careful, you have to check what the computation is going on here before the supplying to the plant. So in reality, put the physical constraint here. What will be the physical constraint? You can say, you can put first constraint as a rate limiter. First constraint is a rate limiter, that how fast your actuator is moving or how slow, and then you put the position. That means you will limit your position 10 degree, for example this case, and 15 degree down this case, or in motor case you cannot provide more than 10 Newton thrust, so you can put 10 Newton upper limit and 0 as a lower limit. And now you will put actuator dynamics, actuator dyna, you can put here this block is actuator dynamics, actuator dynamics, because we know that this aircraft is a plant, but this actuator is also has some kind of dynamics, right? That can be modeled using first order or second order, we have already discussed, right? And then finally supply to the plant. then finally supply to the plant. Okay. Then supply to the plant. So this is all these three are physical constraint. These all three is physical constraint: rate limiter, position limit, and actuator dynamics. Later you will see I will include the delay also when I will go in the aircraft autopilot design part. Aircraft longitudinal, lateral, and directional autopilot design case. Delay is a very important part which actually tell you whether your system is how much robust. And delay in the sense what I am trying to say, here you will take feedback, right? So it will take time to reach here. Computation is going on, right? Here it will take some time to compute. Okay. So this, if you sum up all the delay, then you will get one final delay that you have to include in your model in order to go into the more practical design. Because if you model in the simulation like this, you will be close to the reality. When your product is ready, that will be, your result will be more close to the reality and promising. So thank you very much for attending this class.